Okay, like everything is fine. Okay, welcome to the afternoon session of the OCaML meeting. So the first talk is about Buck2 for OCaML users and developer, and this will be an hybrid presentation by Shayne, Fletcher here and Neil online. And who's starting?
I'm starting. Can you see my slides and hear me?
Yeah,
I
we hear
can't see
you.
any
That's
video.
fine.
Okay, I can't see your video, but I can hear you okay. So hopefully that's enough. Cool. Shall I go? Yes?
Yes.
Cool. Hi, welcome. So I'm Neil, and with you, presumably at the screen, I can't really see, is Shayne. And we're both from Meta, and we're going to talk to you about Buck2 for OCaML users and developers. So Buck2 is a multi-language, large-scale build system, open source by Meta. So let's unpack those things. So it's a build system. It takes your source code and compiles it to libraries, binaries, packages, other artifacts. It's multi-language in the sense that it works with many programming languages, OCaML, of course, but also Haskell, Go, C++, Rust, Lua, Julia, you name it, is there. It's large scale in the sense that it works with small projects of maybe 10 files, but it can scale up to really large sizes. It's open source in the sense that it's available on GitHub, the exact code, you can compile it, you can use it yourself. And it's from Meta, where for the last 4 years, a team has been developing Buck2 predominantly using Rust. So when we say multi-language, what we mean is that Buck2 has no baked-in knowledge of any programming language. So no programming languages are special. Instead, Buck2 is configured through Starla, which is just a dialect of Python, files which say, for example, this is what an OCaML library looks like, this is what an OCaML binary looks like, this is what an OCaML test looks like. And one of the secrets for the Buck2 rules that really makes the multi-language pop is that rules produce providers. So they say, this is the kind of thing that I, as a rule, can produce. For example, all native rules produce merged link info. And the thing about a merged link info is it says how you can be linked by the system linker. So because OCaML produces it, and something like Rust can consume a merged link info, and the system linker can link it, you can have C++, depending on Rust, which depends on OCaML. And the really nice thing is that Rust and C++ don't even need to be aware of the existence of OCaML. So it slots together and you can get really esoteric language combinations just because everything's built on these providers. The other nice thing about Buck is it's designed for large scale. So millions of files is how we're typically using it. That means there are a bunch of things that you just can't do that you might normally do in a build system. So for example, file watching, you can't just look at the modification time of every file. That would take too long, that would take minutes. So we have to use things like iNotify, or there's a program called Watchman that essentially does iNotify over very large scales. We also have remote execution. So this is the idea that you can take your input files and the command line and fling it to a faraway server, which will run it on your behalf. So that means you can run thousands of OCaML compilations at once. But it also means, because it's kind of hermetic and it's given you all the inputs in a very nice bundled form, that if anyone else has ever run exactly that compilation before, they can just give you the results without even running the compilation, which can be really good if you've got large numbers of developers kind of using the same code base. And then one of the important things for Buck2 is its theoretical power. If you're aware of the build systems a la carte paper, it's got monadic or dynamic dependencies. So the idea that the build graph can depend on the output of actions. And this is really important for OCaML because, say you've got an OCaML library with 10 dependencies, they will usually have some internal structure of import statements between them. And that structure needs to be reflected in the compilation commands you access, and it needs to be reflected in the build graph. So how are we going to do that? Well, in Buck1, which was the predecessor to Buck2, what it did is it ran OCaML'23 once and really, really crossed its fingers that you didn't change too much in the dependency graph. And if you did, you had to kill the build system and restart. In Bazel, which thankfully is a little bit more principled than Buck1 was, you have to describe the internal structure of those libraries. So that means as you're refactoring, you have to do more work to keep the build graph consistent with the source code. Buck2, however, has monadic dependencies. So what it can do is it can run OCaML'23, extract the makefile from it, and use that to be the dependency graph. So concretely, you end up defining that you say in advance that the OCaML library will produce the CXMA. You then run the OCaML'23 tool to produce the makefile. You can read that and pass it in StyleArc to produce a graph. You can fill in the OCaML compilation commands in this graph, which will still exhibit the maximum parallelism, and say, well, I'm still producing the CXMA file I promised you I would, but here's the piece of graph that does it. So this gives us very good OCaML support. I will hand over to Shayne.
Can you hear me?
Yep.
Awesome. Okay. Okay. So to start, let me say that in the Buck2 GitHub repository, all of the examples that we see in the slides are there. Also, let me also say that we've entered into the practical part of this presentation, whereby we're about to explain what you write in the equivalent of your makefiles, we call them Buck files, in order to express rules that build OCaML programs. So here's our very first Buck file. It contains two targets, one an OCaML library called Hello World, the other an OCaML binary called the library is called Hello World lib, the binary is called Hello World, and there is a dependency of the OCaML binary on the OCaML library. Of course, in OCaML, we have the choice of producing native code artifacts via OCaML opt, or we can produce bytecode artifacts via OCaML C. Buck is capable of producing either. By default, it will produce native code. You can instruct it to produce bytecode by using what we call a subtarget, the bytecode subtarget, utilizing the syntax that you see on the second Buck run invocation there. By the way, I should have mentioned, these are, let's say, command line Buck invocations that we're reading there. The first one will build and run the Hello World executable from the previous slide, the native code version. The second one will build and run a bytecode variant. Also on the slide at the bottom, we see the use of this -- show output flag that you can pass to Buck, which will cause it to print precisely where the built artifact is in your file system, which is sometimes useful. Okay, so the Buck2 prelude comes with a fundamental set of rules for building OCaML programs. This slide enumerates them all. Pre-built OCaML library we'll look at in a moment. OCaML library, OCaML binary we've already seen. OCaML object, this is using the OCaML compiler together with partial linking to produce a .o, which can be then linked with C or into a C program. The last one, OCaML shared, this is for producing CMXX files, which are so-called plugins, which can be loaded by the dynlink module. They have some niche uses, but we won't discuss them further in this talk. Of course, any real OCaML development, you're very quickly going to want to integrate with OPAM. You want to bring in third-party OCaML libraries. And this slide provides the ingredients for how you can achieve that. Basically, in your project, have a folder, something like third-party OCaML, and within that folder, have a couple of symlinks pointing into your OPAM directory, and then you can write a Buck file that describes the contents of your OPAM or the things that you want to use in your OPAM as pre-built OCaML libraries. What's a pre-built OCaML library? Here is an example. This first example is part of the definition of a pre-built OCaML library for the PPX lib. As you can see, it includes details like, in terms of those symlinks that we saw on the previous slide, relative to the directory that contains this Buck file, where to find the CMI files for PPX lib. What is the path to the CMXA for PPX lib? That's what a pre-built OCaML library definition looks like. The second example shows how to make use of that definition in a library of your own that you are defining for yourself. PPX record selectors is an OCaML library consisting of the well, we don't show the sources involved in that library. The key point is its depths. Depths include this third-party OCaML PPX lib. Okay, so that's roughly how you get that done. OCaML is so rich. OCaML', menher, how do we make use of these? Well, the answer is just throw your MLL files, your MLY files, straight into the sources for your target, and Buck will work out what to do with them, invoking OCaML', menher as appropriate. Similarly, interfacing with C, it's not uncommon to have stub files written in C that you wish to combine with your OCaML. Jolly good, just put those .c files in your sources list and the right things will happen. PPX programming in modern OCaML is ubiquitous, so let's cover how we achieve that. The right-hand side of the slide, record selectors.ml, gives you the gist of a PPX. It generally consists of a bunch of code to do some sort of AST transformation and ends with a couple of statements that register your code with PPX lib. The left-hand side of the slide shows the definition of an OCaML library with the dependency on the PPX lib that we just looked at a slide or two ago. And then we have an OCaML binary, which depends on that library that we've just defined, that combines that library code with a little bit of PPX lib driver code to produce a binary, which we have called PPX. So the next question is, how can we make use of this PPX that we've just defined? And the answer is, well, it's in the compiler flags. We in this example, we wish to run to elaborate the source of the target PPX record selectors test using the PPX that we defined in the previous slide. To do so, we indicate that in the compiler flags for this target by passing -ppx. And here's the key bit of notation: $exe target : ppx. This induces a dependency of this OCaML binary on the PPX that we defined in the previous slide. And it causes the PPX to get executed at the appropriate points in the build cycle so as to, well, do the transform. And whilst we're here, let me also quickly mention that there is an expand subtarget that you can combine with that ---- show output flag that I pointed out before, that enables you to bring up in your editor the elaborated source after PPXs have been applied in this fashion. So that's it, how to use and define PPXs. Now this is where Buck2 really shines, combining different programming languages together. I mentioned OCaML object before. In this instance, we have a scrap of OCaML which defines a Fibonacci function. So it's just one source file which we compile into something that is a bit like a library. It's a .o that ends up in an archive. So fundamentally, it's some kind of library. But it's everything that you need in order to be able to execute OCaML code from, let's say, a C++ program or a Rust program. And that's indeed what we do in the second half of this slide. We have a CXX binary, a C++ binary, which calls OCaML from C++ in this fashion. So this is how we embed OCaML in C++ and other programming languages. Extending, very similar concept. Here now we wish to extend the OCaML programming language from another programming language like C++, and just to be different, this one's done in Rust. I can't read that from here. This says camel print hello. It's a function in Rust using the C ABI. that is then linked into an OCaML binary. So now we have OCaML calling Rust. How do we define the Rust library? Well, we use the Rust library rule. And OCaML binary we're already familiar with, but notice in the depths that we just depend on this Rust library in this very obvious way. Okay, and I'm going to conclude this section with a brief discussion of something else that's very important in modern OCaML, which is wrapped libraries. Dune will do this for you by default. A wrapped library to refresh what we need to know about it. It's basically the idea that for our clients, we enforce that if I'm producing for something, a package called mylib, and it has modules A and B, I should like it that my clients are required to say mylib.a, mylib.b, so that we don't just have these, we don't, to reduce namespace collisions or to eliminate namespace collisions. In order to achieve this, we need a little bit of compiler support, and the way that we do it is we make use of so-called type-level module aliases. So here at the top of the slide, we define an interface file that declares these aliases. Module A is aliased with mylib __ A, etc. Now, where we would normally have a.ml, we instead have mylib __ a.ml, which defines the contents of the module A. And within that module, you can refer to undecorated names like A or B. Mylib.b __ b.ml implements the B module, and the client, when it becomes time to execute functionality from mylib, is required to say mylib.a or mylib.b. There's no other way to get at the functionality contained. And this is the basic idea of a wrapped library. Now, how do we go about doing this? Well, it turns out that the OCaML language manual describes the procedure for producing these things. And really, this is just a transliteration of that web page that describes that procedure. We have an OCaML library that we have called mylib __. It consists solely of that module alias map, and it is compiled with a couple of special flags, minus and no alias depths, and disable warning 49, which I think is something in life. It doesn't matter what it is. But those two flags are kind of required. Then we have a second OCaML library that depends on that first OCaML library. Notice that. It consists of the implementation modules mylib __ a and mylib __ b. And again, it's got some funky compiler flags, minus no alias depths, disable warning 49, and also minus open mylib, which is like saying open mylib at the top of every source file. OCaML dep also requires a bunch of flags, notably a minus map argument, which contains that module alias map that we defined in the MLI. And that, amazingly, will produce a simply wrapped library. Now, what's really neat about this, of course, is we did not have to crack Buck open to add support for wrapped libraries. It's just right there. We just do it in Starlark. And of course, this is a particularly simple example of a wrapped libraries. Real wrapped libraries with masking are a bit more complicated because the user will provide the mylib.mli. But they can be done. It's a similar procedure, just a bit more convoluted. And the last point I'd like to make about all of this is it's all low level like this for exposition purposes. What you would do in practice is wrap all this up in a Buck macro, in a Starlark macro, call it OCaML wrapped library or something like that, which will ultimately resolve to rules like this. But I just want to point out that this is not the end game. You can make it look a lot slicker and make it a lot easier to use ergonomically. Okay, thank you very much. Back to Neil, please.
So briefly, we did some benchmarking against Dune as a standard thing. So for something like Pyre, Buck can do a full remote build in about 12 seconds if it's all just caching. Otherwise, Buck2 is a bit faster than Pyre and a bit slower than Flow. We suspect this is just some tuning of threads, and we plan to investigate more on this in future. And with that, any questions?
Can you hear me? Thanks for the.
Say easier if one of you chooses who's going to answer, and then I can switch it because I don't know if it'll be both.
Yeah, let's hear the question, and then we can work out like who's best positioned to answer it.
So thanks for the talk. It was really interesting.
Thank you.
Are you aware of work to automatically translate Dune projects to?
Yes, I completely failed to mention that. I'm so sorry. There is a GitHub repository called OCaML scripts. It's in the Facebook organization. It was developed by a colleague of mine at Meta. It's pretty experimental, but it works, but it does what you would hope. It scans your OPAM directory and it generates a Buck file for you. So it takes all of the hard work out of like constructing these things for yourself. It's pretty enabling. So the answer is yes.
Okay, so it doesn't work by reading the Dune specification. But
no, it doesn't. No, it does not work by reading the Dune specification, because consider what's in your OPAM. OPAM has a long history. Well, OPAM itself has a relatively short history, but the contents of OPAM have a very, very long history, going all the way back to make, OCaML build, Dune, and any variety of like ad hoc shell scripts, or it's complicated. But findlib and the metadata associated with OPAM can be used to, you can query that like a database, and you can use that to produce these pre-built OCaML library definitions. If it were all in Dune, one could write a program that read a Dune specification and output a Buck specification, which would be even better, because now you wouldn't have pre-built libraries anymore. Everything would be built from the bottom up by Buck, but unfortunately that's a little out of reach just now, but maybe in our future we can hope for that.
Thank you.
You're welcome.
Great talk, thank you. In your example, you showed how to use PPX using Buck2, but the example you showed, you only have one rewriter or one driver. Did you have experience using multiple rewriter or driver?
Oh, yes.
Because in Dune, I think what they do is they link multiple library into one executable and just apply that executable to the code.
You are, Neil, if you're okay, I'll take this too. It's dead straightforward. Just for simplicity's sake, I showed how to define a PPX lib and then link it into an executable. Okay, but we could have had any arbitrary number of PPX libs linked into that. That executable could have consisted of a whole set of PPX transformations to be applied and compiled into one executable, and that is in fact in general what we do. So it is consistent with what Dune does, as I understand it as well. So the answer is yes. You can have as many of them as you like.
So many of us quite happy with Dune.
Yes.
If you have to identify like one killer feature, like if your project uses that,
yes,
use us versus Dune.
Very good question. Neil, please.
Oh. Cool. So I would say the killer feature is probably multi-language support. So if you've got Rust, Haskell, and OCaML, Dune is probably not going to cut it anymore. And then something like Buck2 would be more appropriate. Or if you're trying to use Dune at very large scales, like tens of thousands of files, that's where probably Buck2 would start to shine more.
That's exactly it. Multi-languages and big builds.
Yeah, well, kind of follow-up question. What kind of usage do you have for that inside Facebook?
Neil?
I mean, in terms of big builds, millions of files. In terms of language usage, we have OCaML that has Rust, that has C++, that has Python scripts, that has HTTP downloads. I don't think we've got OCaML and Haskell talking to each other yet, but I wouldn't be surprised if it happens. Because Buck2 is so compositional, we don't really know what plays with what. It's not something people explicitly do. Everything just tends to work together on its own.
So on bigger projects, Dune usually starts to have a bit more trouble building the build graph. And so your startup, when you want to build a big project, is always slow.
Right.
Is it the case for Buck2?
Not in my experience, but once again, I'll defer to Neil to explain why it's so good at that.
I mean, we're used to doing hundreds of thousands of nodes on our build graph all day long. So that kind of thing is perfectly normal, doesn't phase us, has been very well optimized. It's multi-threaded construction of the build graph. It's minimal invalidation. It's just something we're quite used to, so it's well optimized for it. So no, not a problem at all.
I think maybe, Neil, it's worth calling out that at least with respect to OCaML, Buck2 did significantly better in terms of analysis speeds over Buck1, as I recall. One of the biggest criticisms of the implementation of the OCaML build rules in Buck1 was how long it took to like get things started up. It took 60 seconds before deciding it had nothing to build. Come on. But Buck2, it's like almost instantaneous, like nothing to do. Thank you.
Thank you. Shayne, now here.
Thank you very much.
Thank you.